Swayam Prabha. Digital India. Educated India.
And the first problem that we are studying is sampling uniformly from a stream without knowing its length. So, has anyone has any answer about how we can do it? Okay, so let's do it. So, here is the algorithm. Let me write the algorithm and then I'll explain. So, say so suppose the input is say I1, I2 to IN. Suppose this is my input I1, I2 to IN. Of course, it is coming from a streaming fashion. I don't know N. So, I1, I see I1 first, then I2, then I3 and so on. And now I am writing an algorithm. I have a variable called item where I am just storing I1 for now. And now for I2 onwards, and I have another variable called count, which maintains how many items I have seen so far. So I have seen only I1, and so count is initially to 1. Okay. Now output will be one of this item, and the guarantee that it's distributed uniformly at random from I1, I2 to IN. Okay. Now while there are more items, that means we haven't reached the end of the stream while there are more items. So let some item prime is the next item. So the next item I am storing it in another variable item prime, and with probability some P1 with probability P1 replace probability P1 with probability P1 you replace you override the item with item prime. So at the end of the algorithm we are going to output the whatever is stored in the variable item. So you override the existing item with the current item with some probability P, and if you that's it, and this is end of while. This is end of while. And here you just do return item. So is the algorithm clear? Let me explain the functioning of the algorithm. You first see item I1, and you store this item in in a variable called item, and then you see item I2, and with probability P you store item I2 in variable item, and with probability 1 minus P you leave as it is. Again, whenever you see next item, item 3, again with probability P you overwrite the item you have, and with probability 1 minus P you just leave it as it is. Sure? And you and just keep doing this. So at no point you don't need to at no point you need to know the n. You need to know you don't need to know n. And you need another line here, that here you have a count variable. You just do count plus plus. So count variable maintains the number of items you have seen so far. So, and this number of items can go up to n. Of course, you don't know n, but it can go up to n, and so the variable count can be stored in log n bits, and you have log n bits. Sure? Any question regarding the functioning of the algorithm? It's not, I haven't proved yet why this algorithm is correct, why it outputs a uniformly random item from the stream. That I am yet to prove, but any question regarding the functioning of the algorithm? You should be able to write a C code with this pseudocode. Sure? So let's, and this algorithm is completely specified unless just without this P. So I just need to tell you what is the value of P, and then you can write the C code and run it. Sure? Yeah, let's see what calculation does, but let's go step by step. If I tell you the value of P, what to put in P, then the algorithm is completely specified. Okay, so now let's do the analysis. Okay, let's find out what should be the value of P. What should be the value of P? Can any guess? No, we don't know the number of distinct items. Okay, so let's find out what should be the value of P. So can anyone tell me what is the probability that that the algorithm outputs the last item, IN? It's P? No, the last item. What's the probability that the algorithm outputs the last item, IN? I claim it's P. Whenever it reads the last item, IN, with probability P, it overwrites the item, otherwise it doesn't do anything. And only if it overwrites, it outputs the last item. So, first observation, algorithm outputs IN with probability P. Anyone don't agree with this? Sure. So then, and what is the requirement? With what probability the algorithm should output IN? Uniform, that means 1 over n. Sure. So that way it tells you that P should be, that means that P should be 1 over n. But you know, I don't know n. How can I put n there? How can I plug P equal to 1 over n in my algorithm? I don't know n. And not only that, if I don't know n, and if the length of the input was n minus 1, if the stream had stopped at in minus 1, then the correct p value would have been 1 over n minus 1, not 1 over n. Had it stopped at 50, after 50 items, the correct p value would have been 1 over 50, isn't it? So So just imagine this scenario, just see what is going on. So when I am at I2, I have seen the second item. If so, then what should be the p value? It would be 1 by 2. At the third item, p value should be 1 by 3 and so on. So isn't it the p value is 1 by count? Looks like. Because if it is not 1 by count, then if the stream stops there, then the algorithm is not correct. So p value should be 1 by, so therefore p should be 1 by count. Sure, and that sort of matching with our initial condition. We are storing I1 with probability 1 after seeing I1, and that's matching with 1 over count. So if I set p equal to 1 over count, at least for the last item I have the right probability. Whenever the stream stops, at least for the last item, it is output with probability 1 over n, 1 over the length of the stream. But how about other items? It turns out that for other items also the probability is 1 over n only, but that is a proof. So what we have, and that's easy, that's not difficult. So by putting p equal to 1 over count, we have ensured that probability that output equal to In is 1 over n, isn't it? Let's prove that probability that output equal to In minus 1 is equal to, I need to prove that this is also 1 over n. Let's calculate. Let's see when for output to be n minus 1, what event should happen. At n minus 1th step, the item In minus 1 should be at least selected. So that happens with probability 1 by n minus 1, right? And in the next step, at nth step, it shouldn't get overwritten. That happens with probability 1 minus 1 over n. Again, the item In minus 1 should get selected at n minus 1th step, and in the nth step, it should not get overwritten. That only this, if both these two happens, then only In minus 1 will get output. And so this, let's calculate this. And this is right. Let's do In minus 2. This item first has to get selected at n minus 2th step. That happens with probability 1 by n minus 2. It shouldn't get replaced in the next step, which happens with probability 1 minus 1 by n minus 1, and it also shouldn't get replaced in the nth step. Let's see. Sure. And the same thing goes on. Let's now do the generic case for any ij The item should get selected at the jth step. It should not get replaced in the next step and the next step. And again same kind of cancellation happens and only 1 over n remains. And this algorithm is formally called reservoir sampling. Its item is like a reservoir where you are storing the items and you are keep replacing. Any question regarding the functioning of the algorithm or the analysis of the algorithm? Whenever you want to sample uniformly at random from stream, for example, we discussed just the voting scenario, right? We told that sample L votes uniformly at random. How will you sample if it is input is coming from stream? You need this thing to sample, isn't it? Just look at our previous any algorithm which samples. For the sampling task, you need to use this. So a fun exercise. This is for uniform sampling. So an exercise for you. Modify the reservoir sampling algorithm so that the ith item gets selected with probability say pi. Maybe you can take this as 1 over 2 to the I. And since you don't know n, it's so and given or not given, assume summation pi I equal to 1 to n is less than equal to 1. So if it is strictly less than 1, with some probability you don't output anything. So for in this case, if you set pi to be 2 to the I, then the total probability p1 plus p2 plus up to pn is not 1. It is 1 minus 1 over 2 to the n minus 1 or something like that. I think it's 1 minus 1 over 2 to the n. Yeah. So yeah. So with some probability you don't output anything. Just modify the reservoir sampling algorithm so that you have this. Question. Before we move to our next topic. What? Yeah, that's an exercise. Yeah, you see, yeah. Yeah, try to design an algorithm with generic algorithm with pi. Don't use 2 to the I, just pi, and do the analysis. Okay, now let's move on to our next topic. If you don't have any question. So, yeah. So now with this reservoir sampling, you can implement the same sampling algorithm, sampling based algorithm, prediction algorithm in a streaming fashion also, right? For example, suppose there are let me see, let me tell here. Yeah, look at this theorem. So, if you have m candidates and n voters, then with this much sample, the 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 winner here, the most frequent item here is same as the most frequent item in the original votes. Now, try to apply to the scenario that where a router wants to know what is the most frequent destination in the IP packets that it sees. Now, you have the sampling algorithms, but this algorithm assumes that the input is not coming in a streaming fashion, so it can sample in a usual way. But in a streaming setting, like in IP packet network routers, input is coming in a streaming fashion, and then you just do the reservoir sampling to sample this many votes. How will you sample this many votes? You just run L many parallel instances of reservoir sampling. Then each reservoir sampling algorithm will give you one sample each, and then you have L many samples each drawn uniformly at random from the population, isn't it? Okay, so now we are doing quite a few probability just for a change of taste. Let's do some topic of different flavor. Let's do sorting. So let's do sorting. Okay, so we know there is something called comparison based sort. So what is a sorting? Sorting is that we are given say n numbers, and we want to sort them either in non-decreasing order or non-increasing order or something like that. Sure. Now I'm changing the setting little bit, and let me write the setting. So we are given n items, say A1, A2 to An. So in usual sorting we are given n numbers, but here we are giving n abstract objects, and we want to arrange them, but in what order? So the order is decided by the oracle. So there is a oracle. So here is the oracle. If you give two of these items, say AI and AJ, as input to the oracle, it will tell you whether AI is greater than AJ or AJ is greater than AI in some way. So for numbers you don't need this oracle, you just compare their values, but for abstract objects there can be some weird way of defining this, and that ordering is based, oracle is doing this. You just, because for numbers if you look at insertion sort, what are basically you are doing, you are comparing what one number is greater than other or not, right, greater than or smaller than. Those comparisons oracle will do for you for these abstract objects. Now once this oracle is given, suppose it is given as a function which you can call, then you can implement any sorting algorithm, because in usual sorting algorithm, bubble sort, merge sort, quick sort or anything, whenever you need to compare two things, which one is better or which one is greater or smaller, you just call oracle and it will tell you. Perfect. So everyone with me that with this oracle we can implement any classical sorting algorithm. And what is the time complexity for say insertion sort, to sort n items? N square, big O of n square, and for merge sort it is big O of n log n, and yeah. Are we assuming? Yeah. So there is a true ordering, and and yeah, it respects that. It means the oracle don't answer in a way that that creates a cycle, that A1 is greater than A2, A2 is greater than A3 and A3 is greater than A1, then that is not an order, it is a cycle, then the oracle is faulty, oracle is not consistent. So, oracle is okay, it is answering based on some order. Yeah. So, coming back, March sort, they have n log n worst case time complexity, and there is a very beautiful proof which shows that if your algorithm is comparison based, then n log n is what you can hope for. It is the best what you can hope for. You can't go beyond n log n. You can't go little o of n log n. You can't have little o of n log n. I encourage you to Google this result, and there is a in Wikipedia article you can read the proof. There is a very nice, beautiful proof based on decision trees. Yeah, but let's assume that we can't break the n log n barrier because of that lower bound. Okay, now now here is my new problem. My new problem is I am given given m oracles. I am given m oracles, oracle 1, oracle 2 up to oracle m. And I want to know the inherent ordering of oracle 1, inherent ordering of oracle 2 and inherent ordering of oracle m. Sure. So, for example, in the previous case, if there is only one oracle, that's why there is only one order based on which the oracle is answering, and I want to know that order. In this case, I have m oracles. M oracles, they individually give answers based on their ordering of the objects, and we want to know all the orderings. What is the ordering of oracle 1? What is the ordering of objects for oracle 2? What is the ordering of objects for oracle m? Sure. So, let me give a motivating example why we need these things. So, suppose we want to decide on where we will go for dinner, and there are some 10 exciting restaurants, but we should decide on this in a fair manner. So, we ask everyone, what do you ask some say person 1 that what do you think, what is your top choice among these 10 restaurants, what is your second choice, what is your third choice, what is your ranking based on the ranking of these restaurants based on your choice. So, that is the oracle of first person. Similarly, I go to second person, he or she may have a different ordering, different preference, different choice of the restaurants, and so on. Every people may have their different own choice of ordering of the restaurants. So, think of oracle as those persons, and I want to know the ordering of every person. I want to know the choice or preference of or ranking of the restaurants for every person. That is exactly this job. Think of oracles or persons, and I am asking him, okay, which restaurant you prefer between A and B, between C and D, which do you prefer? Those are like queries. He can say, I prefer A greater than B. When I ask between C and D, what do you prefer? He can say, I prefer D over C, and so on, based on his or her ranking. And this way, by asking these queries, we want to learn their rankings. So, so our cost. So, usually we measure efficiency or cost in terms of times or number of steps in my algorithm, but here in this case the cost will be number of queries asked. Sure. And because of that n log n lower bound, I ask n log n queries to the first oracle to know its order. I have to ask second oracle also n log n queries, to know its answer, and so on and so forth. So total cost is theta m times n log n. Everyone with me? Now my goal is to, can I reduce this cost? Can I have something better than or less than mn log n? Obviously, if I don't assume anything more, because of this lower bound, I have to ask n log n queries to every person, and there are m person. So I need to ask m log n queries. So let's put some more assumption. And here is one popular assumption that we put here is single crossing. What does it say about what do you mean by single crossing? What is this extra assumption? It says that you arrange the oracles in this order, that this is oracle 1, this is oracle 2, sure, you arrange them this order, and their rankings can't be completely arbitrary. If you look at, if you take any two objects AI and AJ, then either all the oracles says that AI is greater than AJ, or all the oracles tell that AI is less than AJ. Either they are all telling same thing, or if they are telling different thing, then suppose oracle 1 is telling AI is greater than AJ, and suppose oracle M is telling AJ is greater than AI, then so there has to be at some point where a transition happens from AI over AJ to AJ over AI, right? Means maybe till here everyone is saying AI over AJ, and from next person says AJ over AI. Of course, it can again toggle, it can toggle many times, but this single crossing assumption says that it toggles only once. So it's an assumption on the input. Your input can't be anything arbitrary. Sure. So what is the assumption? There is an ordering of the oracles, oracle 1 to up to n, and if I look at any pair of alternatives, pair of objects, either all of them agree, all of them say one is greater than other, there is no difference, and if there is difference, then there is only one crossover based on this ordering. Oracle 1, I won't change this ordering. This ordering is fixed, oracle 1, oracle 2 up to oracle n. I won't change the ordering with the oracles. So that's the single crossing ordering. And it turns out that many of our real life applications actually has this sort of assumption. Think of an example where, again let's look at the example where, so we want to decide whether Indian Railways should be subsidized or not, or yeah. So suppose we want to decide that, and then there may be a correlation because between our choice. So for example, maybe I think that yeah, it should be subsidized. Maybe some other person thinks that no, it shouldn't be subsidized, and so on. And there it has been shown that this sort of opinions has correlation with the economic level where I belong. Maybe my monthly income. If I am poor, then maybe I want subsidy. If I am rich, I don't want subsidy. So that economic level or monthly income decides this ordering of oracles, decides the inherent ordering of the persons, and when you move along this ordering from say poorest to richest, then there is only once the decision toggles. So when you start from poorest, they keep saying that yeah, subsidy should be there, and at some point it toggles, and from there onwards to the richest they tell that subsidy shouldn't be there. So, these are the kind of applications usually when we have preferences, and these objects on which we have preferences, they are directly correlated with one variable, in this case money, or there is only one variable with which it is correlated, and then you can, based on that variable, you can order the persons or order the population, and this sort of assumptions then often holds. So, that is the motivation for having this kind of assumptions, and if we now assume this assumption, then we can do substantially better than mn log n. Let us see what we can do. Let us see how we can know every orderings without asking so many queries.